Well, looks like we can get started. Welcome back, everyone. So we had a pretty easy time last week, but not really, especially if you opted out from Book Bubble. It's been kind of horrendous. But I think I have a couple answers. It still doesn't look like a whole lot of firm solutions, just a lot of things to try. So it's not the most exciting thing. But any questions or comments to start us out, folks, before we discuss the book bundle opt-out options? Okay, well, with where we're at, we're going to take a look into this last example in 13.1. And then section 13.2, we're going to just look at different kinds of conditions. That is really weird how that's moving. I'm not touching the mouse. Let's move this one over here. There's another mouse, but it's hard to use this one on the actual tray. That's just really weird. Okay, it's holding still now. Okay, so with that fixed, we're going to finish off the last example here. And then in section 13.2, we're one section away for showing what the full confidence interval procedure is going to be in this chapter. So that's going to be our major capstone of chapter 13. And just another reminder, our quiz number 8 got a huge shift. We're just moving it to this current week. That means the due date also got moved forward by 7 days. So this one's due October 30th. So now, before we start off class today, we're going to just take a look at what information we know so far about the book bundle. Some people have achieved getting through all of it. I think Jess is the first one to make that happen. Thanks for sharing all the tips and tricks that you had to pick up along the way.
It was a lot.
It really is a lot. And I have some crazy emails that are like 30, 40 deep where people are going backwards and forwards, not even really figuring out the problem. But I think the major problem, as I understand it right now, is the bookstore manager is getting a promotion, training his replacement, and a bunch of things are just kind of falling on the wayside. That looks like that's what's actually happening right now. So that's not really exciting, but at least it's the truth. That seems to be what ISU is struggling with as a university at the moment. So to take it from the top, here's the best instructions I have so far. So this has been updated, has a revision. If you opted out of the book bundle, then this link probably doesn't even work for you. Even if you've got everything figured out once again, it probably still doesn't work. Thanks for double checking for me. They may have fixed something down here on this link to make it work, but I'm not gonna cross my fingers on that necessarily. So if you opted out of the book bundle, first take a look at this link. Is it working? That would mean it's working. Awesome. So eventually, once things get going, that will go back to working again. That's good to hear. So first thing you might want to do is just click on this guide. What the guide is telling you to do is immediately go to bardsandnobles.com. That's what the link is supposed to have done over here when it said buy now. But I believe it just takes you to this kind of page. And this is extremely confusing once you go here. It's not giving you a great indication of where you're supposed to go, what you're supposed to do, or anything like that. So let's do it ourselves. We would want to go to find your course materials. It's right here. I think I have step-by-step guides on where to look for those next steps. So go find your course materials, clicking on this link. And this will be on the recording, so you can come back to this and play it on YouTube if you need to. Oh, geez, and you have to sign in. Well, they're not going to let me do much if I don't sign in, I don't think, but let me see how far I can go. You have to literally click on the Idaho Falls campus, or else they're not going to sell you anything. It's a little weird. Once you click on the Idaho Falls campus, you have to select the term. So this will be fall 2024, opt out. Prices are the same either way, but I think this is the best way to go. It's just more descriptive, so that could potentially solve problems on its own. The department should be the math department. Easier to just type in math, I think. And then at this point, there's not a lot of options. So the course number is found right here on the Moodle website. So it's this for the course number, that for the section number. We're section 11. So 1153P. And there should only be one option at that point, section 11. Oh, weird. Yeah.
Section 10.
You know, what they probably did is they fixed it after the fact when you're looking into this. Everything was being sort of corrected during the hellstorm of emails where people are figuring out stuff was broken. Mm-hmm. So after all of this, you can click on retrieve materials. And this is what it shows for us. 3 items, and this is really confusing. Only one of these 3 items is going to work. And our department secretary even threw out an email to the bookstore manager. No reply has been given back from that, so we're not expecting much. But not even the secretary could get the bookstore to tell us the difference between option 1 and option 3. No one can tell us, so that's really weird. But what we know for sure is this is the one that gives you back your access to your course materials, my lab and the e-text, if you lost access to that. Not everybody did, which is really weird. This one is if you want an actual, well, I'm really not sure what this is for. You're going to rent it only. It looks like it's probably a hard copy, potentially a virtual copy, but this is not going to help us out at all. We have to go for this option right here. So click add to cart, and eventually I can't go too much further. Once you check out here, they're going to give you some emails. I believe it's going to contain a access code as part of those emails. So once you get to your access code, what the guide indicates we ought to do is now go to, let's see here. It was go to here, but it turns out, this is bizarre. No one came up with this except for, again, Jess found out in tech support that this is a new document you need to go to. Click on this right here. And this is not the nicest form. It's almost looks like a legal doc. I guess it is a legal document of some kind. They're asking for some kind of information. So what I would do is probably skim that and click on, I acknowledge I read it above. Then they want pertinent information. First and last name, email address used in the course. I think this one is very important, the right email address. Institution name, course ID or course ISBN. I would just go here and grab something like that. That whole line like this.
Except for the number, yeah.
That should probably work for the course ID. So just put that right here. It provides a lot of stuff, the title, the course number, the section number. So that should be sufficient for them. Instructor's name, you could just put in Michael Jacobson. Then have you purchased access to the Pearson product after opting out of the course fee program? This whole document looks like it was invented less than a week ago when people realized they had to figure something out of nowhere. So you'll say, yes, bookstore. Then here you'd probably say locate local bookstore, Pearson.com, etc. Just Barnes and Nobles online. Yeah, that should work out just fine. Then this is the major one. The access code is what you're sent to by your email. You provide them that. Click this box to acknowledge that by not submitting proof.
Picture of your receipt in there. So
wow.
I downloaded the email.
Let's pretend this is the receipt.
With the access code. Yeah, you can screenshot it or you can save it as a picture.
Gotcha. Then click on here. And upload it somehow. Okay, I can't drag and drop it the screenshot unless I make a file, but you put the file here, then I would definitely click on that. So you have a bigger paper trail and click submit. That is the most awful, tedious process, and it's still not necessarily done. You have to wait till they check their numbers, go to their backlog. That's the part I'm going to be watching because I know now in my system where to look.
24 hours. I messaged them. Well, it was Thursday that you canceled class.
Yeah.
At like 5:30. They're open until 10. It was the next morning by about 9 o'clock that they approved all my stuff. So
gotcha.
It wasn't very long.
That's at least the one saving grace.
Yeah, hopefully. But it could be worse now that there's more people with issues. But
yeah. So take a look at this option, see if it works out. Give it a try and let me know if you get into a roadblock at any time. And another option is I have an email for a Pearson loyalty specialty representative type person who can help with tech support. And if you'd like, I can provide them with your email and they'll reach out to you. And they're happy to just get on a Zoom call, just like say this one, either sharing your screen or sharing their screen and walk you through it step by step. So that person will get it done one way or another for sure. Well, any other questions or comments, folks, about that whole god-awful process? Sorry about it. Okay, well, I'm going to double check how things are going on Tuesday. I'll probably be spending a lot of time on Tuesday, just looking at the roster, messaging tech support people again, and dealing with any kind of issues that do come up. So if you run into any kind of roadblock on Tuesday, don't hesitate to shoot me out an email. I'll try to do my best to help out as I can. I might get you in contact with a support person and you might want to share your Zoom stream with them, or we can get on a Zoom call ourselves and just do the best we can with where we're stuck at. But I did want to take a good amount of time today just kind of going over that again, because again, this is not a straightforward process. I have some crazy emails that I almost want to share, but that's considered unethical to throw all your colleagues under the bus, but we'll do the best we can. And probably what I'm going to do at the end of the semester, I usually do this, but I think this is a definite now. At the end of the semester, when we're putting in the final course scores, I'm probably thinking about going into the MyStats lab and just dropping something like your lowest 3 homework assignments. That way, if you just got caught up dealing with tech support in the middle and you couldn't get back to those sections, that's not your fault. And out of fairness, we'll be dropping those. I'll make an official announcement right around here when we determine the number. I'm thinking about 3 of them. But any other questions or comments, folks, about anything whatsoever? Okay, well, where we're at so far, we're in section 13.1. Sorry, question first?
After you get approved,
Yeah.
I was for a while, like all last, like today was the first time I checked it, where the course resources.
Yeah.
Wouldn't work, so I actually had to sign into Pearson to
Gotcha.
get in. But now it says it's fine, so I don't know how long it took them to fix it, but.
That's a really good thing to mention. So another thing on this document here, in case this link becomes broken, like, or just doesn't work like you mentioned.
It used to say just buy now.
Yeah, that doesn't convert to launch courseware. You mentioned logging to the Pearson website, and I believe that's this one right here in step 6. So once you get access going, you can also just go right here, use your same login information to sign in directly through their website in this kind of way.
And then I could access everything after that, so.
Awesome. So yeah, go to this page right here. This is on the last link on that document, up to 6 steps to get this going crazy. And yeah, so that will be a great way to access the course until this button starts working again. Hopefully it's instant, but everything seems to take a little bit longer to get going in this class with their book bundle. Thanks again for mentioning that. Other questions so far? Okay, well, let's start going forward in our section 13.1. Really not a whole lot left to do in section 13.1. So probably the best thing we should do is just kind of review and revise what we were doing right before we went to the weekend. Well, a little bit early on Monday. So a week ago, we got to this part right here. Let me just rearrange some windows for just a moment. There we go. So we were taking a look at the essential limit theorem. It's a really powerful statement, but it's also pretty abstract. So these are good notes to come back to and just read through a second time before doing the exercises in the My Stats Lab program. But essentially what it's saying is, if you have a statistic like p hat, which is calculating the proportion of successes in a sample size n from some population, where the true population proportion of successes is p, then we know 3 pretty incredible facts. The mean of the sampling distribution is p. What that is saying is this statistic is not going to equal p exactly. And the more and more we take samples, we get different values of p hat. But all those values have this as the center. They're all trying to measure one true quantity. And that true quantity is at the center of this distribution. The spread of this distribution is through this formula, square root of p times q divided by n. P is the true proportion of successes by the complement rule. Q is 1 minus P, the true proportion of failures in the study. So we have a mean, we have a standard deviation, and the most powerful statement of all is right here. Turns out P hat comes from a legitimately normal distribution. Well, it is approximate. So part of our goal in section 13.2 is to say, when is that approximation actually good and when is it bad? So we want a great approximation for accuracy. And then this was the last roadblock that we hit. If we're going to actually use the central limit theorem, we have to admit that we're using this in a situation where P is the unknown. Our whole goal in differential statistics is to estimate it. So we go back to this from day 1 of the class. We use our best estimator, P hat. And we take our P hat, and plug it into this formula right here. Our standard deviation is truly unknown, but the statistic p hat is. So if we approximate in this way, sure, this is now just an approximation of the standard deviation, so we call it standard error. As a reminder, it's an approximation, but it's a decent one, and this gets us started. So we call that standard error. And through this problem right here, we're talking about the national result of 44% of students engaging in binge drinking. This is a population parameter, but it's not even the parameter we were studying in this problem. In this problem, we turned to a university administrator who surveyed a random sample of 244 students at a totally separate university. So that's why our parameter P is defined in this way. It's not equal to 44%. So to determine if we really have an interesting result, different than 44%, here's the proportion of successes in the sample. The denominator is the sample size, 244, coming from right here. The numerator is the number of successes, and in this problem, a success means admitting to binge drinking in the past week. Always, we should put a disclaimer on these notes. I won't give a disclaimer every time, but that as a success is a bad outcome. The success just means that's the thrust of the study, the thing we want to learn more about. So we had 96 successes, divide by 244, and that's the sample's proportion of successes, 0.39344. Unfortunately, though, that is not necessarily a good indication the university is different from the campus at 44%. Because essentially, this is what we're doing. We're saying p hat is approximately p. That's the p we're referring to, but we need to say how accurate that is using a confidence interval. So still a lot of work to do, but this is the major part of the work. After we get this portion, we're about ready to describe the confidence interval formula. Calculating the standard error of p hat means first put down the formula. Notice there's p hats and q hats this time. That's just a reminder we're using the statistic up here. So 0.39344 got plugged in here, 1 minus it goes here, and that's our result, 0.03127. And I had a whole cheat sheet for part E, but I think I do recall how this last part goes. This is not a great question for quizzes or exams, in all honesty, but it's one that's asked in WebAssign, and I can't change the parts on WebAssign, so we're going to do it here today. On WebAssign, I keep saying WebAssign, sorry, on My Stats Lab, that's a different class, different platform. On My Stats, this is a multiple choice question, so our job is just to determine which answers have something that's a little bit off, making it wrong. So here's what the interpretation of this would look like. In a random sample, of, this is the tricky part too, we have to use the context. It was a random sample of 244 students at this university. Now, we're trying to give an interpretation of the standard error. So we have to say, what is it even in the first place? It's an approximation of something else, the standard deviation. So that's part of our interpretation here. We'll say the approximate standard deviation for the sampling distribution of successes is approximately 0.03127. So that's our interpretation for this kind of problem. It has to mention the sample size. It has to mention that we're approximating the standard deviation with this new quantity called the standard error. And one thing I'm missing here is it also should mention what the success is. So let's add that as an additional comment. You can kind of see why this doesn't really make a great exam question. It's a huge technical statement. It's more just making sure you understand what this really represents as an approximation. So the next part of the statement should say, Here, a success is admitting to binge drinking. Well, we did it, folks. That's the final write-up of section 13.1. Took a little while to get there, but any questions at all with the conclusion here? Okay, so now that we have the standard error, now that we have the central limit theorem saying we're using the normal distribution, we're going to start stitching these results together. But again, like we mentioned, there's still one critical thing that's left over. It's right here. Sorry for the random scrolling. Right where we said it's approximately normal, we have to justify that a little bit better, give the real conditions where the approximation is good and when the approximation is truly bad. If we can make that happen, then the normal model, when we use it, will know it's accurate, and we'll have better and better estimates for the unknown parameter P in this problem. So let's save this up and now take a look at the assumptions and conditions. So that's section 13.2. Let me get these windows going for us. Okay, this just takes a moment to get everything right where it should be. There we go. So the notes start out pretty similar to how they started out before. We just have the central limit theorem. But here are the assumptions and conditions that we mentioned. Our major work in this set of notes is just check different scenarios, see if the assumptions and conditions are met. So our examples here are pretty similar to what you're going to see in the homework set as well. One thing we're going to do at the very end of the notes, though, is we're going to call back to the 68, 95, 99.7 rule. Just this once. We're not going to make this our official procedure, but this will help us connect the dots even further and show how all of this work, starting in, say, the chapters with the normal distributions, now connect to the confidence interval. So we are about ready to derive the true method. But first, we have to know when the method works, and that's the assumptions and conditions. I copied and pasted this whole theorem into these notes because it's weird to have assumptions and conditions unless you're staring at the theorem for which it applies to right away. So right out of the gate, that says for the central limit theorem to be effective, the following must hold. And the first thing that must hold is something we can't even really check, the independence assumption. The individuals in the sample must be independent from each other. So why can't we check that? Well, we would have to be the actual researcher that designed the study, collected the data, interpreted the data. So you can imagine how this could go wrong. Think again about the problem about admitting to binge drinking. And imagine everyone in class today, including the folks over in Zoom. Let me open the Zoom window. Imagine everyone in class today and those participating virtually, you're part of a random sample. Pretend you're not all part of this class. Maybe I selected you randomly and you just all came here for part of the study. And if I put you all in this room and just go down the line and ask everyone, would you admit to binge drinking? A lot of people are going to say no, and your answers are going to affect the answers of the people around you. If the very first person I select is brazen and not shy and says, yes, I binge drink, then that's going to set the tone for every other response. People feel a little bit more willing to share. But if the first person says no, there's a higher chance the next person's probably going to say no, I would say. And that's violating independence massively. So the way to do that study is get a random sample of all of us, but we all have to be interviewed separately. We can't hear how other people are responding and those kinds of things. And the studies we look at, we're not looking at their full methods. You'd have to buy the paper, probably 50 pages long, read how they collected the data, how they collected the sample. It's not something we can really assess. It's still something we think about. But here's one thing that does help with independence. Even if you have random data, you can violate independence terribly. Like I mentioned, interviewing everyone in the same room is an automatic disqualifier. They found out you did that in your study is probably rejected. But if we didn't do anything like that, and your data really came from simple random sample, then there's a good chance that the randomization on its own gives you independence, unless you did something wacky in your study that annihilated it. So randomization helps tremendously with independence. So what about the randomization condition? You know what? That's something we can't really check either without buying the study and reading the whole thing. It's something we have to just take for granted on the write up. Either they're going to say it was a simple random sample, or they'll fail to say so, and we'll just go by the information in the problem. So we'll check that condition there. And this condition is a little bit surprising. This is tied in with independence in a certain way, but for the central limit theorem to really be effective, it actually assumes that your population size is infinite. That's a mathematical fiction, though. No population that we're looking into is infinite in most situations, especially if we're talking about, say, human subjects. So in place of having infinite, as long as our sample doesn't exceed 10% of the population, we are meeting that condition there. So let's imagine we have some weird study where the sample size is maybe 25. If we take that and multiply it by 10, so here's 10 coming from the 10% times n to get 250. If it's plausible to us that 250 is not larger than the population size, then we say we meet this condition. We'll write that out really carefully when we execute that in our problem below. But that's the idea with that one there. And finally, the success failure condition is the one that we can really check the most. So in a real quiz problem, in a real exam problem, you're really going to do majorly these parts here. So these are the major parts. That we can actually check. And it says here, the sample size should be large enough so that the number of successes and failures in the sample are both larger than 10. And let me change the wording here. Let's say larger than or equal to 10. That was written in kind of a weird way. We're trying to allow 10 itself to work. If you're a person that likes formulas, that's what this is calculating. It's saying the sample times the sample proportion of successes. That would just be the number of successes in your actual sample. And it has to be greater than or equal to 10. And as a second formula, this is the number of failures, n times q hat. That has to also be greater than or equal to 10. And let me highlight this right here in red, just to convey, if you printed out the notes, I just include this just to be a little bit more specific. We're allowing for 10 to be the cutoff. I think it was written in a weird way. So those are the assumptions and conditions. If 1 through 4 are valid, then this part right here is a highly, highly accurate statement. Probabilities coming from the normal model can be trusted. Any questions or comments, folks, before we put each one of those assumptions to action? Okay, so here's how the problem goes. Example 1 says, researchers in the development of new treatments for cancer patients often evaluate the effectiveness of new therapies by reporting the proportion of patients who survive for a specified period of time after completion of the treatment. And that kind of makes sense. Cancer is one of those things where you might feel great for a while, but after 3 years, something can come right back. So for this particular problem, it says a new genetic treatment involving a simple random sample of 25 patients with a particular type of cancer resulted in 8 patients surviving at least 5 years after treatment. So for this cancer treatment, 5 years was the benchmark. Survival after there is considered a success in that situation. But let's start recording the information that we know. It said a simple random sample of 25 patients, so that's our sample size, and is 25. I think I spilled the beans a little bit on this one, but let's see. If they said out of 25 patients with that type of cancer, 8 patients survived with at least 5 years of treatment, they're telling us what the success would be. So we can say here, a success is the outcome of surviving at least 5 years after the new treatment. The reason we call that a success is If this part of the problem is indicating the 8 out of the 20 out of the 25 meet this outcome, that outcome itself was the success of the problem. Any questions, folks, with part A? Okay, now here's the exciting part. Part B says, determine if the assumptions and conditions for the central limit theorem are met. So let's just take a big screenshot and run through this information. So like we mentioned, we're majorly checking out condition 3, condition 4. It's impossible for us to really assess independence. So we go off to randomization. So let's begin there. On real quiz problems, real exam problems, this is where you would start as well. You know what, that's worthy for putting on the notes. Let me just, to make the notes a little bit more clear, let's write this out as a more official statement. These are the major parts. To check on quizzes and exams. So we'll be doing 2, 3, and 4. So with that in mind, still, it's interesting to think about independence. The individual samples must be independent for one another. That means whether one of the 25 patients being a success, it shouldn't affect the other patients being a success or not. Would you believe that it would be the case in this kind of situation? A success would be surviving cancer at least 5 years after treatment. And I would say, yeah, most of the time that should be a success. However, there's a way this could fail, really, truly fail. Imagine somehow, some way, all 25 patients, they're part of a study, right? What if an email got linked and they just formed a group? Maybe it's a support group because they all have a rare cancer. They're all doing a rare treatment. A support group just makes sense. If that happened, and then people start encouraging each other, supporting each other, well, their outcomes could be in some ways tied because your state of mind has a lot to do with your recovery and how you can fight off an illness. If everyone's helping out each other, this could influence the success failures, especially if some of the 25 got left out, for example. So there's ways that independence could fail even if we do everything right. So that's kind of surprising and concerning. So we start on 2, the randomization condition. This is the one we can really check. Reading through the problem, it just said right out of the gate, there is a simple random sample. So all we have to say in our problem is part 2, the sample is specified to be a simple random sample. So we have good randomization. In fact, we have the gold standard of randomization. The simple random sample is the best one for our methods. So that wasn't too much, right? We just look through the context and see if we can find that part. We can, then part 2 here is confirmed. Next is the 10% condition. This one could be concerning because we're told this is, let's see, well, I guess I've not seen that statement. I thought somewhere it said a rare type of cancer. It didn't say that, just a particular type. So maybe less of a danger this time. So let's take a look into the 10% condition. This is part 3, and this is a great way to start out. Whatever the sample size is, let's just state it here as part of the work. And for the 10% condition, I'm just going to copy the method our author uses. It's a pretty clever method. Take your 10% and just multiply your 25 by 10. So 10 times n would be 250. So if our population size is larger than that, we have a really big problem. Central limit theorem is not going to give us accurate results. So here we have to make a determination. I don't think it says anywhere that this is a rare cancer. This is just a new treatment. So let's say down here, provided this cancer is not rare, the size of the population is larger than 250. For just about any kind of cancer you can come up with, if it's not a very rare type, there are loads of people suffering from the same thing, whether it's a bone cancer, a skin cancer, and so on. So I think this is a pretty reasonable statement. We don't have more than 10% of the sample, or excuse me, more than 10% of the population in our sample. So we can say here, this condition is met. Notice that 3 is a really tricky one. Depending on how you argue, how you view the problem, or what you just see in the write-up, maybe you really did say a very rare cancer. You might have said because it's very rare, it's conceivable 250 is larger than the actual size of the population, and this condition fails. So as long as you support your answers on this one, that would be an acceptable response as well. Finally, in step 4, this is a little bit more firm, what we can actually calculate. There's no guesswork on this one. This is either condition passes or it fails, strictly based on what the problem is saying. We have to count the number of successes and the number of failures in the sample. Sometimes this is a nice formula, but only if the problem gave you p-hat would I actually use that. It's easier to just simply go back up to the problem and count them. So a success is surviving at least 5 years after a new treatment. It says here, 8 patients survived at least 5 years after treatment. So we get to say there are only 8 successes in the sample. Well, that's a big problem because down here it says number of successes and failures, both of them simultaneously, have to be at least 10 or larger. So the moment we find a failure or a deficient size right here, only 8 of them, the whole method is telling us we shouldn't use the central limit theorem on this problem. Sample size is too low, and the normal approximation is going to be a bad one. So we'll say here, this condition is not met. And that's a firm not met. There's really no way to argue about that. That's a strict condition to use the central limit theorem. And so that causes an immediate failure. But that's okay. We'll just move on to the next problem and hope for the best on that one. We'll say here in part B, overall, the conditions are not met. What we did, folks, that's checking conditions. It's really kind of a weird problem because in statistics, when you're checking conditions, you really need loads of data. But we're students. We're not the ones that designed this study. We're not the ones who published it. We really didn't have any hands on this study. So we are outsiders looking in, just trying to do the best we can running through these conditions. It's not unusual that we have no information on independence. That's more typical than anything. It's not unusual that they didn't say anything about randomization. Doesn't mean it wasn't a random sample, but not every write-up is going to tell us how the randomization went. And not every problem is it going to be clear if the 10% condition passes or fails. That means this is a pretty big problem just on its own, doing an analysis on the context of the problem. In an exam situation, doing this part B, that's a problem, again, all to its own. I would give you a new context. All you're doing is checking conditions. I'd probably give you a part A just to center what a success is. In case there's a mistake, there's partial credit now. But it is kind of a long process to break down context like that. We'll do it again just for extra practice, but any last questions or comments? Okay, just a reminder again, on quizzes and exams, we're not going to really directly comment on part 1, since again, you have to have really very intimate data on how the study was actually designed and executed. So let's now, I guess there's another right up there, we'll just use that. Let's now do the last part and calculate the standard error for these data. This last part is just more of a review. This is a major part of actually doing the confidence interval formula. So we're getting to that major procedure step by step. To calculate the standard error, we first need this thing, p hat. P hat is defined to be the sample proportion of successes. And we know we have 8 successes, so that helps us out. We also know that the sample size is 25 in this problem. That's just enough information to calculate p hat immediately. So p hat is going to be equal to 8 divided by 25 for a value of, let's take a look, 8 division by 25, pretty small number, is a 0.32. So we're getting there. What we want to calculate is the standard error for these data. So the way the standard error goes next is we write it as SE, shorthand standard error. The parentheses right here are using something called function notation. If you haven't gotten into function notation or it's been a while, no worries. The way this is read as is standard error of p hat. The parentheses aren't saying multiply, so we're not multiplying by any number. This whole symbol is just a way to say this long statement. So now the actual formula goes square root, we take p hat times q hat, divide the whole thing by the sample size n once again. By the way, this is a good habit to get into now that we're getting more and more formulas starting in section 13.2, 13.3. Writing this out is really helpful just to kind of practice with the formula. It makes using the formula a lot easier because you're slowly just absorbing it every single time you write it down. So next step, square root of, in place of p hat, we put in a 0.32. But anyone recall what we should write down in place of q hat? Exactly, thanks. We'll go 1 minus 0.32, like you said. Whole thing is being divided by sample size, same quantity as before, 25. So notice the parts that match up. When you calculate the statistic p hat, you have 25 in the denominator. When you calculate the standard error of that statistic, you have 25 in the denominator, but still all of it in the square root. Then this is the fun part where we actually just put it all into the calculator and get a result out. This is a tricky one. Sometimes can make the homework system, MyLab, really kind of not the funnest system in the world. So we're doing it a lot in class just for the sake of practice to kind of get ahead of all that frustration. So if you have your calculator with you today, don't hesitate to give it a try and let me know if you're getting different values. So lots of ways to calculate this. Let's do the order of operations way for the folks that like to go step by step. Start off with the innermost parenthesis and go 1 minus 0.32. Then with the value 0.68, we're over here. We want to multiply it by 0.32. So just hit times 0.32. So it's always a 1 minus, but it's always times something else. And it's always right after divide by something. Hit division, throw in the sample size at 25. And we get this figure, 0.008704. Now we do this step. Made it a huge square root symbol just to emphasize, make sure everything goes in there. But with this process, it's not as much of a danger. Just take a square root of that number. Hit the second button. Right over here is your power 2 button. That's a good one to practice. It's kind of hard to see. There's a square root right to the right of my red dot. You hit that, then up arrow once, and hit enter to paste in the number. That way there's no additional mistake on copying, retyping. And that's finally our standard error. To 4 decimal places, we'd have a 0.0933. 0.0933. Well, any questions at all, folks, coming up with the number? Awesome. So that's so far the process for a random statistical problem where we know we're dealing with categorical data with successes and failures, only 2 outcomes. First thing we want to do is check conditions. Next thing we want to do is calculate these two values and the standard error. After that, we use the central limit theorem over here to get what we'll call a critical number and put it all together. So we're getting very close, just a couple steps to go for the full procedure. But just for the sake of practice, let's try this all over again with emphasis on condition checking. Like I said, for real exams and quizzes, that is its own problem. I'm not going to give a problem that does every single little thing at once because it would carry over multiple pages. That's kind of hard to do in an exam setting. So coming down to this one, example 2, here's our next attempt at this. The setting for this one is really old data from 1974. I think we might have looked at it once or twice in class. And we'll eventually analyze it once we get into section 13.3. It says to evaluate the routine policy or the policy of routine vaccinations of infants for whooping cough, adverse reactions were monitored in 339 infants who received their first injection of the vaccine. From that sentence, all we know is there is a sample size, 339 infants. Next, they tell us reactions were noted in 20.35% of the infants. Notice that's kind of weird in a way. They gave us a statistic right away. Essentially, what this is saying, it's color-coded, is that the sample proportion of successes, p hat, is 0.2035. If that's the case, we should be able to say what a success is. Any volunteers for this one? What is a success in this situation? If you know what it is, but you don't want to say it, I totally understand. It turns out a success is having an adverse reaction as an infant after getting an injection for the whooping cough. So that's our success. The infant had a really, really bad time. I'm not sure what the adverse reactions were, but they're interested in that. They're calling it successes, and about 20% of the sample had an adverse reaction. This was their first injection of the vaccine, and this is probably when the vaccine was very, very new, so they're trying to fine-tune it at that point. So say here, a success is the outcome of the infant having an adverse reaction to the vaccine. I know we didn't say everything. We didn't say what kind of vaccine, what, for example, that we're dealing with whooping cough. So it's okay to be a little bit brief, like we mentioned before. Well, any questions, folks, with the successes in the problem? Okay. Once again, the major conditions we'll check. Let's just say it again here, just to be specific. We'll check these last three. Carefully check on quizzes and exams. Essentially what I'm saying is if you skip the independence assumption check, that's okay in these kinds of settings. I would say it's probably likely these data really are independent, but unless we knew everything about this entire study from start to finish, we really can't justify that statement. So we move on to the randomization condition statement instead. Do we have any evidence or any indication of randomization? Doesn't really seem like it, right? It just says adverse reactions were monitored in 339 infants. No indication at all how they got those infants. We hope it was by random. They didn't just go to some hospital and grab everyone available and injected them. But also keep in mind, this was a real study published in The Lancet in the 70s for sure. I bet you couldn't publish this study in the 70s if it wasn't a random sample. But based on what we know, we just don't know if it was random or not. Having information missing about randomization doesn't tell us that it wasn't random, we just don't know. So let's say for condition 2, it is not known if the data are random or not. So just like condition 1, condition 2 is a total unknown. By writing this down on paper on a quiz problem, essentially all you told me is that they didn't give us any direction or indication in the problem whatsoever. So we just move on to condition 3 next. So condition 3, we have a pretty large sample, 339 infants. But if our sample exceeds 10% of the population size, the central limit theorem will suffer again. I don't think that'd be the case, but here's what you want to write down on paper just to justify your response right here. So take the 339 infants, multiply it by 10, so it's now 10 times 339 equals 3,390. And if this condition fails, the 10% condition, it would be because the population is at that size or smaller. But what is the population in this situation? Sorry, say again? Not necessarily, to be totally honest, but we do know that it's for infants as a population. It might have been all infants in a certain town, a certain city, something like that. But even if it was all infants in, say, Idaho Falls, that's not more than 10%. Would you all agree with that? Or excuse me, pointing at the wrong thing. That would not be more than 10% of the population. And the population for this, because it's a whooping cough vaccine, is conceivably supposed to be all infants on the planet. Everybody should be getting access to that vaccine. So we can say here on this problem, even though we don't know exactly what the population, it is plausible. Let's say very plausible. That the population of all infants is larger than 3,390. Kind of hard to say that number when you're not looking at it, right? So that means this condition passes. Let's say that here. This condition passes. But again, this is a pretty debatable one. If the population for this particular study was, once again, maybe just some small sleepy town, maybe Iona, maybe that is larger than the population size of all infants in Iona. But if it's a larger scale study, which seems plausible for something like a whooping cough vaccine, that'd be on the eyes of the target of lots of governments around the world, this is probably a huge population. Any questions at all, folks, getting through part 2? Excuse me, part 3, the 10% condition? Okay, now we move on to the success failure condition. This one's a little bit nicer because it's just a definite process every single time. But notice what they gave us in this problem was a sample size, 339 infants. They never said the exact number that had an adverse reaction. This is the time at which you really do need those formulas right here that we were looking at and hinting at. Sometimes the problems tell you the number of successes. Other times we have to use a formula like this right here to obtain it. So let's go on to step 4. For step 4, we do have to show some work on this one. We have to give a number, the number of successes and number of failures. So let's organize this way. Number of successes is equal to n times p hat. So that's that formula up here that's highlighted in yellow. We need that to come out larger than or equal to 10. Let's just carry this down so we don't have to scroll so much. So back to our right over here, let's plug in information into the formula. In place of n, put in 339. In place of p hat, Let's just hit that with some highlighting. Let's put in 0.2035. And this seems like it's going to be a pretty large number. That's only because the sample size is pretty large itself. So 339 times 0.2035 gives us that figure. And notice that it's kind of a concerning number, right? Because you can't have 68.985 amount of an infant. That's just a strange number. But that just is an indication this was rounded right here to 4 decimal places. If that's the case, you would want to take this and just round it to the nearest integer. So that would mean round up to 69. So there'll be 69 successes. I guess we said successes right here. We don't need to say it again. One thing that's a good idea to add to your paper is that inequality, just as a reminder that we passed the benchmark. This is indeed greater than or equal to 10, and just a little check to convey we met that condition. That's not the whole story, though. It's conceivable in the right problem that you have the right number of successes, but the wrong number of failures. So we have to check the second equation, n times q hat this time. Any questions so far with our first check? Okay, well, that was such a fun adventure. We'll do it again and say number of failures is going to be equal to n times q hat So when we substitute in the information for this one, almost the same. We go 339 for the sample size n. Only change now is, because it's not p hat to q hat, use the complement rule. P hat is the proportion of successes, so 1 minus p hat, 1 minus 0.2035, is the sample's proportion of failures. So almost the same computation. It's faster to just put it in the calculator than to write it down. So 339, 1 minus 0.2035. And we've got it. Again, we're rounding to the nearest integer, so 270. So 270, which is also greater than or equal to 10. But you know what you could have done now that I've gone through the whole process? You could have said, well, if there is 69 successes, go to your sample size of 339, take away the number of successes, 69, and there's your number of failures, 270. Sometimes that's a kind of a quicker way to calculate. So if you like that shortcut, let's write that down right here. Either use the full formula, or you could say, this is n minus 69 as our shortcut. But in either case, let's take a look at what we have. We have to have at least 10 successes, at least 10 failures. Put a check on both just to convey we found them. There's an awful lot of successes and failures, and so we can say this condition is met. So overall, are all the conditions met? We don't actually know this time. We have to resolve whether the data was random. And if you really, really want to be sure, you have to be like a forensic investigator and track down every single person that was a part of the study, interview them, read all of their papers, figure out everything you can about how they collected this data. And then and only then will you be able to make an opinion on independence or not. That's a really rough thing to get quality data on. But any last questions, folks, on maneuvering through all these conditions? Okay, and just for the sake of it, extra practice, since we haven't calculated the statistic very often, or the standard error, let's do it just one more time. To do that, we need p hat, sample proportion of successes. We also need the sample size. So let me just carry this down. We'll put it just down here as a temporary screenshot so the notes don't get too busy. These questions really are tricky because imagine you're doing this as a quiz problem or an exam setting. You have to know what the standard error is referring to. So it's kind of a vocabulary check all at the same time. If you see standard error, think this, SE for standard error. It's SC of p hat because this is categorical data. It'll be the square root p hat times q hat divided by sample size n. And now from this point on, we're just plugging in our information. So in place of p hat, put in 0.2035. Place of q hat, 1 minus 0.2035. Divide the whole thing by the sample size, which was the 339. Okay, I think we are done with this information here. Any questions at all in putting it all together? Okay, so back to the calculator. For the folks that like to do it all in one shot, here's how it would look. I'm a fan of this process, putting this whole thing in a single line, because if you make a mistake, it's easy to just go up arrow on your calculator and make whatever changes you have to make. So go top to bottom, left to right. Verbatim put in the way it's written, 0.2035, parenthesis 1 minus 0.2035. Close the parenthesis, immediately hit divide, and type in sample size, 339. Your calculator should look like this. Where that bar is by the red dot is the most critical part, because it's so easy to let 339 come outside of the square root by accident. So if everything is going along according to plan, you should be getting that number. So to 4 decimal places, we have a 0.2187. Oh, thank you for spotting that. It looked right at first until you mentioned it. Let me try again. 0.0219 actually is what that would round to. 0.0219 to 4 decimal places. Thanks for the help on that one. Well, we got it, folks. That's the standard error. You might be wondering, why are we calculating the standard error on these notes if it just ends right at the step? It's because once you get the 68, 95, 99.7 rule going, and you're working with the standard error, we're ready to derive an actual confidence interval for the unknown population proportion P. The way it goes is about like this. Let's grab the 68, 95, 99.7 rule and just take a look at it. Let's plug it into the notes. Where did it go? This would be 5.3. All the way back over here. This will be as good of a screenshot as any. Let's dump that on the notes. Right here. Actually, I want a little bit more. The picture's nice, but I think what helps connect the dots as well are these statements right below here. So let's grab them. I'm just gonna, this will work. So here's the 68, 95, 99.7 rule. Here's some statements down below that go along with that rule. Let's make this just a little bit smaller. And here's where it gets really interesting. By the central limit theorem, the mean is P itself. And this normal model, the normal distribution, this would be the sampling distribution of P hat. So our statistic P hat comes from here. If our assumptions or conditions really work out, then this normal model is accurate. Again, that's extremely surprising. Our data is categorical in the first place. And what does it say? Approximately 95% of observations are within 2 standard deviations of the mean. Remember when it says mean, they are talking about P. That's the thing that's unknown. We're about ready to estimate it, but here's our next problem. We do not know the standard deviations at all because not only is P unknown, the formula for the standard deviations involve P. So we approximate it. Standard deviation of P is written this way. It's approximately equal to the standard error of P hat, which is by this formula we used a couple times on these notes. P hat times Q hat divide by N. So we have a lot of major things going for us. We have the center, it's the mean P. the sample proportion of, the true population's proportion of successes, it says the statistic p hat comes from this normal model, and 95% of the time, p hat is within 2 standard deviations of p, is what this is now saying. So let's say this all together for one overall statement. A 95% confidence interval for p. That's important to put that p there. That's the unknown, the parameter, the population's proportion of successes. We're going to that 95% because we're going to approximate with this much accuracy. We're going to go 2 standard deviations away from the mean. So here's how it will go. We take p hat. That's our best guess at the unknown p in the first place. Then we're going to add and subtract a certain value. The number 2, that's our approximation. We're going to make that a little bit more accurate. Add or subtract 2. We can't put in the actual standard deviations, so we put in the standard error instead. SE p hat. So this is the 95% confidence interval for p. It contains 2 things. We always know that p is approximately equal to p hat. We knew that from day 1 of the class, but this is done a little bit more. This confidence interval for p says, if you add 2 times the standard error to your statistic p hat, and then subtract 2 times standard error from your statistic p hat, you're going to get an interval of numbers for which 95% of the time, the unknown parameter p is within your interval. So this is a method that works 95% of the time. We call this portion, the part that we're adding and subtracting, the margin of error. This is one of those unfortunate election years that we're getting blasted by a whole bunch of stuff in the news and the media about statistics. So if you hear margin of error, that's what they're talking about if they're dealing with proportions, which they often are, because a success might mean you're voting for one candidate, a failure is you're voting for another. That's this exact model right here, measuring proportions. So if you hear margin of error, that's how we're estimating the error in that estimate right there, finally. It took just 11 weeks to get to that point. But any questions at all, folks, with the write-up here? Okay, our major goal next class is to put in, let's say it this way. We want a more accurate number. Letting that catch up. It's really weird. It kind of lags towards the last part of the class. I think I broke Word again. I'll try to say, just in case you're complete your notes, we want a more accurate number here, is what I'm trying to say. I'll put that in eventually, but it could take a while for Word to become a little bit more normalized. Clicking on it did not help. But any questions or comments, folks, before we call it a day officially? Okay, when we come back next class, we'll be in section 3.3. Still have to write the notes, but shouldn't take too long. Have a great evening, folks. And I'll be emailing and checking out things on Tuesday, really first thing in the morning, trying to figure out a little bit more about our book bundle problem. So if you get random email, that's probably why.
If you want a more accurate number, are you saying of the 2 or of a?
The 2 right here specifically. It's going to be about 1.96 if you're curious. And what we're going to do is use the calculator inverse norm to be more accurate. Push over here. Yeah, it's the one right over there, 220. Yeah, I'm there 2:30 to 4:30. Yep, you bet.
Yeah. No, my word. I can't go over something, so I won't. I know. You wanna blow something up? No, I don't want to. I don't have something. Who fixed it?